All right, guys, welcome back to part 3 of section 3.2. It's the longest series regarding one section of the textbook ever created. So the last theorem that was cut off at that last video concerned the second theorem in section 3.2, that is Rolle's theorem. And it is really the same exact theorem as the mean value theorem. It is really just a special case of the mean value theorem. So let me give you a drawing and show you how this theorem applies. We'll start out with a continuous and differentiable curve, so it's smooth and continuous. No sharp turns, no jumps, no vertical tangent lines. And you are going to be given an interval. We'll call this from A to B. And here's your f of A, and here is your f of B. Rolle's theorem states that if this curve is continuous and differentiable and the slope between the endpoints is 0, so that is a horizontal line, so you have a slope of 0, then there exists at least one point C in between A and B such that the slope is also 0. So, excuse me, if you have a differentiable and continuous curve between A and B, and the slope is not equal to 0, that is the mean value theorem. Rolle's, again, is the special case where just the slope between the two endpoints is actually 0. You work it exactly the same as you do the mean value theorem. You're just checking to make sure that the slope is 0 between the two. Now, I don't know why they split it off into two separate ones. It's really the same theorem. Let's go ahead and work through a problem. And we'll do everyone's favorite, some trig. So you got y is equal to the sine of x going from 0 to pi. And I want to know if Rolle's theorem applies, and if so, I want you to find the value of c guaranteed by the theorem. So we're going to go through this exact same steps as we did with the mean value theorem. First of all, we're going to check continuity. Is it continuous over the closed interval from 0 to pi? And the sine is a continuous curve. There are no vertical asymptotes. There are no place where this function is undefined. So we know for a fact that going from 0 to pi of the sine of x is in fact continuous. And again, you're just acknowledging the fact that it is continuous. Now what we're looking for is differentiability over the open interval from 0 to pi. And to check that, we'll just take the derivative. So that's f prime of x is equal to the cosine of x. The derivative is in fact continuous from 0 to pi because the cosine is continuous from 0 to pi. So, continuous and differentiable, which means you are guaranteed a value of c between 0 and pi, where the slope is equal to the line that passes through the two endpoints. So again, just like the mean value theorem, what I need to do is generate two ordered pairs. So I'll start with the left-hand endpoint, 0, and I'll plug that into the point machine. That is the sine of x. That gives me 0. I will then plug in pi into the point machine. That's the sine of pi. That's also 0. Now these y values don't necessarily need to be 0, they just need to match. Like for instance, you could have something like 0, 8, and pi 8. As long as these y values match, the slope between them will be 0, because as we know, the slope is nothing more than the change in y over the change in x. So you got 0 over pi, which is in fact 0. So again, as long as the y values match, you're good to go. All right, let's get rid of this. And in order to find the value of c, I take the slope that I just found, which in this case was 0, and I set it equal to the slope machine. And then I just solve for x. So I arc cosine both sides, and I get x is equal to pi over 2. There's more places where the cosine is equal to 0, but I'm only looking for the value of c that falls within this interval from 0 to pi. So that is my value of c. It is pi over 2. And of course, you could have more than one value of c. Those will all come out algebraically rather, when you solve this equation right here by setting the slope equal to the slope machine. All right, so long and the short of it, Rolle's theorem is exactly the same as the mean value theorem. Best of luck, guys, and I will see you guys next week. Thank you.